All right, so when you have a balanced reaction, we need to balance it for two reasons. One, so that it makes sense, right? I can't create an oxygen atom. I can't destroy a carbon atom. So I have to have it balanced so that it makes sense. It doesn't violate laws of science. The other reason I want to balance it is because these coefficients are useful to me. They tell me relationships, which we kind of talked about at the beginning of class today. They tell me the number of individual atoms that need to react. So if I want to react one oxygen, I need 2 carbon monoxides. They also tell me the relationship in moles, which is even more useful usually if I'm doing calculations, right? If I have so many grams of oxygen, I want to know how much CO can be converted into CO2. If I want to know something quantitative about a reaction, I'm pretty much always going to need these coefficients to tell me the mole relationship between one substance and another substance. We saw some examples where that is the case already. This particular reaction is very useful because carbon monoxide is very poisonous. It binds to the hemoglobin in your blood and prevents oxygen from binding. And then you suffocate because you don't have oxygen binding. So, since combustion reactions do produce some amount of CO, we don't want to breathe that in, your catalytic converter in your car allows extra oxygen to push that CO into CO2, which is much less dangerous. And it's not going to bind to the hemoglobin in your blood, so you don't have to worry about that. So this reaction is important. You need to be able to recognize, how much oxygen you need if you want to convert CO2 or carbon monoxide into CO2. So the balanced reaction tells me 2 moles of CO, because of the 2 here, requires 1 mole of oxygen to react with it. And if that happens, I'll get 2 moles of CO2. So I can say 2 moles of CO2, or 2 moles of CO is equivalent to or equal to 2 moles of CO2. This is a relationship. The relationship between moles of one substance and moles of another substance comes from whatever those coefficients are in the balanced reaction. We can use that to do all kinds of examples. So look at this simple example. I want to react 3.82 moles of CO. How many moles of CO2 will be produced? Well, if I want to know how many moles of CO2 will be produced, and I've got 3.82 moles of CO, I need a relationship between this unit and this unit. That relationship comes from the balanced reaction. It comes from the stoichiometry. So anytime I want to cancel moles of one substance and get moles of a different substance, anytime generally I'm converting from information about one substance to information about another substance, I'm going to need this mole relationship. I need a balanced reaction, because whatever the reaction is will have its own specific coefficients to balance it. And those coefficients become the relationship between moles of one substance and moles of another substance. So in this case, when I multiply, I just get the same answer, but that's just because the ratios or the coefficients happen to be the same for those two substances. That's generally not going to be the case. So if I want to relate one substance to another substance, I need that relationship. So if I want to relate it to the oxygen, I want to say, how many moles of oxygen do I need to react with 3.82 moles of CO? Well, I need to cancel the moles of CO and get moles of oxygen. So that comes from their coefficients. So 1 oxygen is only needed for every 2 COs. So in that case, when I cancel this, I'll take 3.82 and I'll divide by 2. So that'll be 1.91 moles of O2. Questions about that? So these types of relationships are really important. We use them to solve all types of problems. So here's another one. So urea is a byproduct of metabolism. Urea is the chemical that gives urine its name. So urea is this chemical here. It's produced when ammonia reacts with CO2. You can make it in the lab that way. So what if I want to calculate how much urea I can produce if I start with a certain amount of ammonia? If that ammonia reacts fully, well, I just ask myself, what's the amount of urea? Or how many moles of urea can I make if I start with 5.25 moles of ammonia? Again, keep the substance with the unit, because moles of one substance is not necessarily the same as moles of another substance. In this case, when I balance the reaction, 2 moles of ammonia are needed for every 1 mole of urea. So that's my relationship. If I want to cancel moles of ammonia and get moles of urea, 2 ammonia for every 1 urea, and so that allows me to cancel and get the units I want. Normally in the lab, we'd be measuring things in grams. But we also know the relationship between grams and moles. We did a lot of calculations involving that this morning. Right? So if instead of starting with moles, if I started with grams, I just get the molar mass from the periodic table, convert it to moles first. So anytime you want to convert information about one substance to information about another substance, you've got to convert to moles first. Because the only relationship you'll ever have between one substance and another substance is moles to moles from the balanced reaction. You've got to convert to moles first. Use that relationship to convert to a quantity of a different substance. Another example here. Here we are working in grams, so we can do an example that illustrates that. So here I want to calculate the mass of ammonium nitrate, which is this reactant, that I need if I want to produce 10 grams of nitrous oxide, which is laughing gas. So maybe I want to make nitrous oxide this way. So question I'm asking is, how many grams of the ammonium nitrate, the NH4NO3, do I need to make 10 grams of N2O? Again, I have information about one substance. I want information about a different substance. No matter what, I'm going to have to convert to moles, whether I'm starting with grams or liters or whatever volume I start with. I have to convert to moles to relate one substance to another substance. So to convert to moles first, grams of N2O to moles of N2O, I need the periodic table. So I take 2 nitrogen, 2 times 14.007, plus 1 oxygen, 15.999. That's going to give me 44.01 grams per mole. So that gets me to moles of N2O, but the point is to get information about a different substance. The reason I'm converting to moles first is because I can use the coefficients in the balanced reaction. In this particular example, they happen to be 1 to 1. There will be many examples where they're not. So whatever these coefficients are, they come from the balanced reaction. Now I've got to the substance I want, but I'm interested in grams, so I just need the molar mass of that substance. Oops, NH4NO3, 2 grams of NH4NO3. So I would use the molar mass of that from the periodic table. That has 2 nitrogens, 4 hydrogens, and 3 oxygens, and I get 80.05 grams per mole. So now these cancel. I've got the unit I want. So then I just plug into my calculator 10 divided by 44.01 times 80.05, and I get 182 grams. Nope, 18.2 grams. So this is powerful. It allows me, if I ever have a reaction occurring, if I want to make a certain amount of product, I know how much reactant I need to put in by doing this type of conversion. how would I figure out how much water is produced? I would do the same thing. To figure out how much water is produced, I would start with the same first step. Because if I have information about one substance, I want information about a different substance, I need to convert to moles first. So in this case, I want to cancel the moles of N2O and get moles of water. That is a 1 to 2 relationship. So 1 mole of N2O gives me 2 moles of water. And then if I wanted to get to grams, 1 mole of water, because if its mass is on the periodic table, is 18 grams of water. So then I would just put that in my calculator. Right, so this relationship is really important. It allows us to convert information from one substance to another substance. We can also do this reaction involving gases, right? Because gases, the moles of a gas can be calculated by the ideal gas law. So if we have information about a gas we can relate to moles, then if I know how many moles of gas I have, I can tell how many moles of these other substances would have been needed to produce that gas because of the balanced reaction, the coefficients in the balanced reaction. So that's what this question's all about. How many grams of Na2O2 do I need to put in if I want to make a specific amount of CO2? Whatever amount of CO2 I have, it's got to be in moles. Because if I want to convert information about one substance to another substance, I have to convert to moles first. So I will use the ideal gas law to figure out how many moles of that CO2 I have. So I would take standard temperature and pressure. The standard pressure is 1 atmosphere. Standard temperature is 0 Celsius or 273.15 Kelvin. The volume that's given is 1 liter. And I know R is a constant. And so I can cancel Kelvin, cancel liters, cancel atmospheres. That will give me moles. So it's going to be 1 divided by 273.15 divided by 0.08206. 0.0446 moles of CO2. So this is nothing new, right? This was pretty much what we did in chapter 11. So I can use the properties of a gas to figure out how much gas is there. Now I know how many moles of one substance. I use the balanced reaction to tell me moles of any other substance I want in the reaction. So if I want to cancel the moles of CO2 and get moles of Na2O2, relate one substance to another, I use the coefficients in the balanced reaction. This time they happen to be the same, so they'll cancel mathematically, but that often won't be the case. And then if I want grams, then I need the molar mass. Right? I would add 2 sodiums, which are basically 23, and 2 oxygens, and I get 78 grams per mole. So here everything's canceling except the unit I want. And so I would just multiply that, and I would get 3.48. Questions about that one? If you're able to follow these and understand why I'm putting the steps together, that's a great start. But to be able to do them on your own requires a lot of practice. So you want to be practicing a lot on these. Hopefully you would have already been practicing a lot of conversions from chapter 5 and chapter 11, but we're adding really one key new element, and that is this step. So you want to do a lot of examples that incorporate that new step to make sure that you can get through them effectively. I think we have just one more example here. So this is another practical reaction, and this reaction is used on a submarine to remove CO2 from the atmosphere, because as the sailors are breathing out, they produce CO2, and if that accumulates too much, then that becomes a hazard. So they need to scrub that or remove it from the air. So lithium hydroxide will pull that CO2 out of the air. And the CO2 will be just bouncing around randomly. If it collides with the solution of lithium dioxide and moves into that solution, if it collides with enough energy, it will react, the electrons will be rearranged, and it will be produced into CO3, which has a charge of 2-. So instead of CO2, the lithium hydroxide adds another oxygen onto it. With that extra oxygen on the carbon, instead of CO2, now it's CO3. Now it has a charge. So with this charge now, it's attracted to other particles. It won't break those attractions and go back into the air. So it'll remove it effectively from the air and make it into a solid. So what's happening here in this example is we have a total volume of the submarine. That's given. We have a temperature. So we assume the sub's about room temperature. So if we convert that to Kelvin, 298 Kelvin. That's temperature. It's telling us that the pressure is going to drop as a result of removing the CO2. So similar to an example we did this morning, if we want the pressure just responsible for the CO2 removed from the air, that's going to be the pressure that was created when that CO2 was present minus the new pressure after the CO2 has been removed. So that would be the pressure of the CO2 in atmospheres that's removed. So the question is, how many moles of CO2 were removed? Well, if I want to know how many moles were removed, moles of CO2, that should be equal to, from the ideal gas law, the pressure of the CO2 times the volume divided by the temperature divided by R. So the atmospheres cancel, the liters cancel, Kelvin cancels, I got moles. So 0.0079 times 2.5 E5 divided by 298 divided by 0.08206, and I get 81. Got to round to 2 sig figs because I only have 2 on the 0.0079. 81 moles of CO2. If I wanted to know how many grams that was, I would just use the molar mass of CO2, convert it from the periodic table, convert it from moles to grams.